Okay, yes. Okay, so also a brief reminder of the Schwinger model, the one flavor and two flavor version, and then I will show you some results that we obtained for the Schwinger model at 0 temperature, the spectrum for the one flavor case, and the temperature dependence of the chiral condensate, and then I will move on to the two flavor case where we have the sign problem. So it's a demonstration that indeed these methods can overcome the sign problem. And then also some results in the non-Abelian case, the spectrum and entanglement entropy. And this is based on these 5 papers that you see on the right side. And you can also have a look at the recent review, which is the proceedings of a very nice plenary talk given by Marie Carmen in the previous year's Lattice symposium. Okay, these 5 papers that you have seen on the previous slide are by far not all that is happening. Here it's over 30 references. Probably it's still very incomplete, but you see that it's a very active area of research to use these methods or related methods to lattice field theories. Okay, the motivation for doing this work comes mostly from the sign problem that you encounter in the traditional approach to lattice QCD. So you have the path integral. It works in Euclidean space-time, and if you are interested in static properties at 0 baryon density, you do not have the sign problem, and this has led to tremendous successes of lattice QCD with many computations at the percent level of precision or even per mil. But if you want to do real-time dynamics, then basically you cannot say much. Basically, these methods cannot work then. If you want to do finite baryon density, then you encounter a sign problem. It can be a mild sign problem if your chemical potential is not too large, but it can become really severe if the chemical potential is larger. And of course, this is a region of great physical significance. We would like to explore the QCD phase diagram from first principles, and right now, using Monte Carlo simulations, one cannot do too much. So one can nicely probe this region here at 0 baryon density. It has been established beyond doubt that there is a crossover from this hadronic phase to the quark-gluon plasma phase. You can also go a little bit into this direction to explore a bit this area of the phase diagram where the chemical potential is not too large and the sign problem is pretty mild. But what you have here is basically it comes from some models. We do not have first principle information about this part of the QCD phase diagram, and of course this is really relevant to try to explore this. So there are some ways to alleviate the mild sign problem, which come under the names of reweighting, Taylor expansion, or analytic continuation. But these methods are basically hopeless if you try to go into this area of the phase diagram. For example, to find the critical point, or not to mention the conjectured color superconductivity phase. There are also smarter ways, for example, Lefschetz symbols or complex Langevin, and they have led to interesting progress, and I think there are still good hopes to obtain nice results from this. There are also some dots in both methods, so there are more methods, and depending on your worldview, you could put them as smarter ways, or you can put them in the hopeless ways. So I will not comment on this. So still, definitely, some alternative approaches are needed, and one of these alternative approaches is definitely tensor networks, and this is what we wanted to explore in this project. So now a reminder of the Schwinger model. It's our main toy model for our applications of tensor network methods. So it's the simplest gauge theory with matter, but the physics is still surprisingly rich. It resembles in several aspects more complicated theories, and QCD in particular, like confinement, the chiral symmetry breaking, or the non-perturbative generation of the mass gap. That was actually the motivation of Schwinger to introduce this model over 50 years ago. The massless case is analytically solvable, so you have the opportunity to do precise checks how well your methods or algorithms do, and as such it has become really the standard toy model for testing lattice techniques and new algorithms. Our formulation of the model is pretty standard. You could hear from David yesterday how this is formulated. So one goes to staggered discretization to get rid of the one doubler in one spatial dimension, and one also does the Jordan-Wigner transformation to have spin 1/2 variables instead of fermionic variables. Okay, here you have the full formulation of the multi-flavor Schwinger model. I don't want you to analyze this in detail. I just want to tell you about the terms. So there is the kinetic term and its Hermitian conjugate. So these have a form of a psi plus, the sigma plus, sigma minus. And here we put every flavor on a separate side. So the flavors hop only on the sides of this flavor, and between them you have a string of sigma z's. Then there is an inhomogeneous offset, side-dependent, and also an inhomogeneous magnetic field, side-dependent. And finally, there is this sigma z interaction on arbitrary distances, and this is the gauge term. So this is a long distance interaction. So the gauge part is basically, it gives rise to a long distance interaction. And also one more thing, if you want to include the chemical potential, it comes very easily. So it's absolutely not more difficult as we have in the Monte Carlo methods. Okay, so now to the results. Our first work, we wanted to test these methods in the one-flavor Schwinger model, whether we can reproduce the spectrum, the ground state, and the lowest excitations. And here is an example how the spectrum can look. You have the ground state, then you have the lowest vector state, and then we have open boundary conditions, so we have a bunch of vector excitations, and finally at some point we get to the second particle of the theory, the scalar. To obtain continuum results, we have to go through a series of extrapolations. So we have to investigate the bond dimension dependence, and you see that it converges very well. The largest bond dimensions here are 140, and you see when you compare this number here and the numbers here, you see that we are relatively converged to something like 10 to minus 10 or 10 to minus 12 already with bond dimensions of order 100. Then we also need to do the extrapolation to infinite volume. And finally, the continuum extrapolation. This variable here, 1 over square root of x, plays the role of the lattice spacing. And you see this is linear in the lattice spacing with some corrections. Here, I think we did quadratic as far as I remember. So we have results with very good precision, and therefore we are sensitive to corrections like order a squared or even higher order corrections, as you will see in a moment. And in the end, we got some numbers for the vector mass gap, for the scalar mass gap. The vector case was actually done before in the language of the DMRG, and you see that these results are compatible. And for the scalar case, they are, in that case, this is a comparison with an older strong coupling expansion result, which was not very precise. Okay, now a few words about thermal properties, our next thread of research. So to compute thermal properties, you have to calculate the thermal density operator, rho. which is the exponential of minus beta times the Hamiltonian, where beta is the inverse temperature. In the matrix product operator approximation to this thermal density operator can be computed using imaginary time evolution acting on the identity matrix. Basically, one divides this thermal density operator into exponentials with Hamiltonian times a small step, and then one uses a second order Trotter expansion. We have these terms in the Hamiltonian, and it turns out that these terms, the hopping term and the mass term, they are easy, so to say, that they can be represented by an MPO of a small bond dimension 4, while the gauge term, this long distance term, is more problematic. And one can proceed by using a Taylor expansion, and this gives results here. So you have a solid line, which is an analytic result, and our result is in red. You see it agrees pretty nicely, apart from maybe this region that was a bit of a surprise for us. So this is the region of high temperatures. And therefore, we also used a second option to truncate the MPO by allowing the electric flux to be only not larger than some value of L cat. So then the bond dimension is related like this to this L cat. And when we did this, it turned out that also this high temperature region, this is reproduced very nicely and with smaller errors. So this is the practical way, the truncation of the electric flux rather than the Taylor expansion. Okay, and here I think an interesting lessons for lattice QCD practitioners, how the continuum extrapolation looks like. So at low temperatures, it turns out it's pretty what we expected. So this is linear in the lattice spacing, and there are also expected logarithmic corrections to this order A scaling, sorry. Yeah, but then when we looked at the high temperature, and this was one of the reasons why the results with the Taylor expansion were not very good, we could not go to fine lattice spacings, and therefore we did not have enough data for proper extrapolation. You see here that actually we are sensitive to quadratic corrections and even to cubic corrections. So the final fitting ansatz that gives good compatibility with the analytic results has to be cubic, and this gives you good chi-squares of the fit. So it becomes really complicated at high temperatures, and having these precise results, we have to go to a complicated fitting ansatz to reproduce the correct result. Okay, so now I move on to the case where we would encounter the sign problem in Monte Carlo simulations. In one flavor model, you do not have a sign problem. Basically, there the physics does not depend on the chemical potential, so it doesn't make sense to introduce this. In the two-flavor case, we would have a sign problem in Monte Carlo, and our observable of interest was the difference in particle numbers of flavor 1 and flavor 2. And there is an analytic computation in the massless case done by Narayanan. Here you can see the analytic result. These different curves correspond to different temperatures. There is no zero temperature, but you can imagine, I think, that this becomes just a step function. For this temperature, it's not really a step function. It's rounded here, but at zero temperature, it becomes a step function, and you have first order phase transitions at 0.5, 1.5, 2.5 in this variable, which is the so-called isospin chemical potential, the difference between the chemical potentials of flavor 1 and flavor 2. So here is an example of our results. You see indeed that we have some jumps at some positions. These positions here do not have to be at 0.5, 1.5, 2.5, and so on, because we, of course, still have some lattice effects. So we have to extrapolate them out. So this is how we can find the positions of these first-order phase transition. We can write the energy like this, and we have a term proportional to the total chemical potential and to this isospin chemical potential. And when we subtract from the energy this first term, you see the slope of the data gives us this delta n, this observable of interest. And from intersections of these red lines, we can extract the positions of the phase transitions. Okay, so here are the continuum extrapolations for a few cases. And finally, it leads to some numbers. But basically what you see here, in the massless case, we agree with these expectations of 0.5, 1.5, 2.5, and so on within the error. You also have the volume, because we also have some volume dependence. Okay, maybe it's better summarized here. Especially you can see that at large isospin chemical potentials, you have some dependence on the volume, but when your L times G becomes 6 or 8, there is no longer any dependence, and we reproduce this analytical result. We also did it in the massive case, and here you see more dependence on the volume. And this is all summarized in the phase diagram, the fermion mass on the x-axis and the isospin chemical potential on the y-axis. Here are these 0.5, 1.5, and so on. And there you see that at finite fermion mass, things change a bit. Okay, so now I move on to the non-abelian case, the SU2 in 1 + 1 dimension. So the Hamiltonian looks very similar to the Schwinger model case, but now we have, of course, the SU2 instead of U1 gauge variables. So we have the kinetic term and the mass term, and finally the color electric energy term. Okay, so these operators U are SU2 matrices, and they can be interpreted as rotation matrices, and the Hilbert space for each gauge link is analogous to a quantum rigid rotor with total angular momentum J. It can be described in two reference frames, the body fixed frame and the space fixed frame. And then one can introduce the quantum numbers corresponding to the z components of the angular momentum of the rotor L and L prime, and we have the total angular momentum J. One can introduce these variables L and R, which can be interpreted as a left and right electric field on a link. Then you have the J squared in terms of the L's and R's. And this leads to the conclusion what is the suitable basis for this problem. So we have on sides, we have the fermionic occupation numbers of color 1 and color 2. And then on the links, we have the J, L, and L prime. Okay, and we have the Gauss law. So the physical states have to satisfy this Gauss law, where G can be expressed in terms of these L and R variables and this non-abelian charge Q. Okay, so for the abelian case, one can actually integrate out all the gauge fields. So when one has the incoming flux through the boundary and the matter content, then one does not need anything else. For the non-abelian case, it's no longer possible, but still one can drastically reduce the Hilbert space of the link. And instead of working in a basis containing the full color information, one can restrict oneself to a basis formed only by color singlet states. So the Gauss law actually takes the form that if you know the electric flux on side K, and if you know the matter content on the next side, then your flux on the next side is either the same, if your matter content is 0 or 2, or it can differ by 1 quantum if your matter content is 1 fermion. So in the abelian case, it would be really unique. And here you have these two cases that if you have one fermion, then J can change by plus or minus 1/2. Okay, and then in addition to reducing the degrees of freedom that you have in the problem compared to the full basis, the color singlet basis also gives you the possibility to trivially truncate the color electric flux at a certain value of J max in a gauge invariant matter. And then if you restrict yourself to states with J not exceeding some J max, then you have a truncated model with Hilbert space of dimension D-link equal to 2J max plus 1. And of course, it's an open question that has to be found out experimentally. What is the value of J max? Then one needs to really have the full SU2 theory. This we cannot predict. Yeah, if we only take J max equal 1/2, this will correspond to a quantum link model. And if you want a full SU2 theory, then you probably have to go higher than this. And we will see how far we have to go. Now it's pretty interesting where you compare the full basis and this color singlet basis. What is the okay, thank you. What is the dimension of the Hilbert space? In the full basis, you have 5, 14, 30, and 55. And in the color singlet basis, you have 2, 3, 4, 5. So it's very important in case someone wants to implement this on a quantum computer, then of course it's much better to use such a color singlet basis and have these dimensions. Okay, this I basically mentioned already. And then we did a series of extrapolations in bond dimension and in the system size. I have to accelerate a bit. We found the ground state energy, which agrees nicely with the analytical result. And we also did the vector mass, the calculation of the vector mass. And here you see the continuum extrapolations, and you see that actually for the truncation at J max equal 1/2, we cannot really properly do the continuum extrapolation. And it's actually not guaranteed that the quantum link model does possess a continuum limit. If we increase the J max, you see the results become much less sensitive to further increase of J max, and probably we are getting to the full SU2 theory. And this is the mass dependence of the vector mass gap, and there is a prediction actually that the mass dependence should take this form with some critical exponent nu. And fitting our data with J max equal 1, 3/2, and 2, we got the values of this exponent nu, and we get a value around 0.7. And it's interesting, actually, there is an analytical prediction for the value of this exponent coming from the large N theory. It was done by Paul Steinhardt back in the 70s, the same Paul Steinhardt that you know from cosmological inflation. And you see that SU2, two colors it's already close to infinitely many colors. That's pretty interesting. Okay, and finally, we did also entanglement entropy. You know how important it is, and here how it goes in the SU2 model. So we can decompose the entropy like this. The last term is the physical, the distillable entropy that you can get with these local operations and classical communication. And we also have a classical entropy and representation entropy that are not physical and result from the Gauss law. And you know, of course, this connection of QFTs with conformal field theories, and the expected value, the expected entanglement entropy should behave, should diverge like this with the correlation length, where C is the central charge of the underlying CFT. So then, taking the continuum limit of this entanglement entropy, looking what happens when we move towards the continuum, we can extract the value of this central charge from the diverging correlation length. This is our fitting ansatz, so we have this term, and we have some lattice corrections, some cutoff effects, some finite term, and higher order corrections. So this is how it looks. These kinds of plots you have seen yesterday in David's talk. Then we also do the bond dimension extrapolation, the infinite volume extrapolation, and finally we get this plot for the continuum extrapolation. And actually it looks quite innocent, right? Looking at this data here, one would not think that it's divergent, so not knowing the theory behind it, one could just try some linear fitting ansatz with some corrections maybe, so maybe a quadratic, and you would not have any divergence at all. Yeah, but this is really divergent, and it gives us this central charge as actually expected. The value is 2, which is what you expect for 2 flavors of Dirac fermions. And you need to go to J max equal around 3/2. So for 3/2 and 2, these are these results. You see they are not distinguishable from each other, and we have this central charge compatible with 2. The J max equal 1/2 has a very different behavior, and J max equal 1 somehow interpolates between these results. Okay. Yeah, so yeah, maybe I skip this. You know that the way to apply all this to QCD is a very long way. The first steps have been taken, but this is of course the crucial step, right? How to go to higher dimensions and finally arrive at QCD. So this is my summary. You see that the tensor network methods can offer you an alternative approach to lattice gauge theories to obtain very precise results, and in particular to overcome the sign problem of Monte Carlo simulations. And we have applied this to 1+1 dimensional systems, including the abelian and non-abelian case. The biggest challenge is definitely to go to higher dimensions. One next step could, for example, be 2+1 dimensional quantum electrodynamics, which would for sure be one of the most complicated tensor networks calculations in history. Okay, thank you for your attention.
Hi, I would like to point out a possible misrepresentation with respect to quantum link models, in the sense that the quantum link models are a superset of Wilson-type theories. So the J max that you have in the quantum link model, it would be the representation of the quantum links. So you can take it half, you can take it 1, 3/2, and so on.
Okay, I meant the simplest one, yeah, so, that one that appeared already in this paper of Horn, like 30-something years ago.
So if you were to take a spin 1 quantum link model, you could take the continuum limit without any problem.
Okay.
Yeah.
Yes, I have a similar question. So can you go back to your entropy calculation? Do I understand correctly that even this one, so even in the J max equal 1/2, you do have a critical scaling?
Okay, here it's actually unclear. For J max equal 1/2, it's unclear whether we can, okay, maybe before we get to the entanglement entropy, we have this vector mass gap scaling, right? And here it seems that we cannot do the continuum extrapolation, that we cannot choose a fitting ansatz that would work. So probably there is no continuum limit here, and how this transforms to entanglement entropy, I cannot really say. There is something non-physical about this case, right? It's not really the SU2 theory that we are interested in.
No, I understand, but does this gap goes to 0 at some place in your parameter region?
We cannot extrapolate to the continuum limit, so we cannot really say, right? Something weird is happening there, and we don't really know why. But we know that it's not guaranteed that it has a continuum limit. Or to put it strongly, probably there is no continuum limit of this theory. If we push it further and try to extract things, if we agree to crappy continuum limit fits, and we extract this exponent, we get 0.64, which is also quite close to the 2/3. But I don't know how reliable is this result. And the same for the entanglement entropy, right? So these are not really good fits, as far as I remember. And so the fitting answers does not work very well. If you still push it and you get the final result, you get something like this. But I'm not sure whether it has any physical interpretation.
So can you just remind us what is the extra requirement beside the fact that you have a critical point that you ask for getting a meaningful continuum limit?
I would say that in the continuum limit, your correlation length should diverge, right? And it should be described by some form of the fitting ansatz that I was showing there. So if the fitting ansatz does not work, I mean, these are precise results, right? So going through the series of extrapolations, you get very precise results. And then if you are at Jmax equal 2, your continuum extrapolation works very nicely, and therefore we believe it's really the SU2 theory. But in the case of Jmax equal 1/2, it doesn't work. So I don't know how physical it is.
Okay, just a comment to Luca's question. Is that this continuum limit that you do is a la Wilson, right? By just taking the large values of the bare parameters. However, there are other ways of taking continuum limits, like, for example, dimensional reduction. That might give up physical information, as happens in some other theories.
Okay, we can discuss this. Yeah, yes. That's interesting.
Just maybe a completely naive question. I mean, it's super nice that you don't have a sign problem in your approach. Naive question is like, what do you precisely mean by this sign problem? I mean, in the sense that, of course, that's a basis-dependent property, and you should think of equivalence classes under local basis change, or more generally speaking, under quasi-local circuits that you could use to kind of conjugate the Hamiltonian with. So what's the take here, and in what sense is it like an uncurable sign problem that you encounter?
So it's just that in a Monte Carlo simulation, you get some probability measure, right? And it has to be real and positive, yes, for it to really be the measure. And then you can see analytically that when you introduce the chemical potential, that this probability measure becomes complex. So it can no longer be used as a
no, that's not my point. I mean, there's like Hamiltonians for which you have no sign problem in the x basis, but they go to the z basis and suddenly there's a sign problem, and so on. I mean, that's what I mean. I mean, that depends on the choice of local basis, whether it's complex or real or even positive. So this freedom one can exploit, and if one can get rid of the sign problem by suitable basis changes, then it's gone, so to say.
Yeah,
have you checked this?
In the path integral approach, you cannot do this, right? So you can do this using these techniques like reweighting or other kinds of techniques, but you will never get rid of the sign problem.
Okay.
It's this NP-hard problem, this paper of Troyer and Wiese, where they show.
Oh, but this is not quite right, this paper. But anyway.
Okay, yeah, that's I'm not touching this. Yes, but it's a difficult problem, right? This we will agree, and it's not clear whether there can be a universal solution.
Okay,
for this.
Thanks.
You can solve it in some cases using some physical property of the system, right? But in general, not for QCD.
Okay, thanks.
Just a quick comment. I mean, it's well known that in 3+1 dimensions, and if you consider QCD, for the case of isospin chemical potential, there is no sign problem.
True. Yeah, but it's not the thing that you can get the phase diagram out of this, right?
No, why didn't you consider just independent isospin chemical potential for each flavor?
You mean our study? So in this case there would be no sign problem, but if you work at your total chemical potential is 0 while your isospin chemical potential is non-zero. But here it also works in the case where the total is non-zero, right? We are not really super interested in what happens in the Schwinger model, but in a situation where you would have the sign problem in Monte Carlo.
Other question? Okay. I think we can go to lunch. And thanks all the speakers.
Thank you.